Chapter 2, Equations and Inequalities. Introduction. For most people, the term territorial possession indicates restrictions, usually dealing with trespassing or a right of passage, and takes place in some foreign location. What most Americans do not realize is that from September through December, territorial possession dominates our lifestyles while watching the NFL. In this area, territorial possession is governed by the referees who make their decisions based on what the chains reveal. If the ball is at point A, X1, Y1, then it is up to the quarterback to decide which route to point B, X2, Y2, the end zone, is most feasible. 2.1. The rectangular coordinate systems and graphs. Tracy set out from Elmhurst, Illinois to go to Franklin Park. On the way, she made a few stops to do errands. Each stop is indicated by a red dot in Figure 1. Laying a rectangular coordinate grid over the map, we can see that each stop aligns with an intersection of grid lines. In this section, we will learn how to use grid lines to describe locations and changes in locations. Plotting ordered pairs in the Cartesian coordinate system. An old story describes how 17th century philosopher and mathematician René Descartes invented the system that has become the foundation of algebra while sick in bed. According to the story, Descartes was staring at a fly crawling on the ceiling when he realized that he could describe the fly's location in relation to the perpendicular lines formed by the adjacent walls of his room. He viewed the perpendicular lines as horizontal and vertical axes. Further, by dividing each axis into equal unit lengths, Descartes saw that it was possible to locate any object in a two-dimensional plane using just two numbers: the displacement from the horizontal axis and the displacement from the vertical axis. While there is evidence that ideas similar to Descartes' grid system existed centuries earlier, it was Descartes who introduced the components that comprise the Cartesian coordinate system, a grid system having perpendicular axes. Descartes named the horizontal axis the x-axis and the vertical axis the y-axis. The Cartesian coordinate system, also called the rectangular coordinate system, is based on a two-dimensional plane consisting of the x-axis and the y-axis. Perpendicular to each other, the axes divide the plane into four sections. Each section is called a quadrant. The quadrants are numbered counterclockwise as shown in Figure 2. The center of the plane is a point at which the two axes cross. It is known as the origin or point 0, 0. From the origin, each axis is further divided into equal units, increasing positive numbers to the right on the x-axis and at the y-axis, decreasing negative numbers to the left on the x-axis and down the y-axis. The axes extend to positive and negative infinity as shown by the arrowheads in Figure 3. Each point in the plane is identified by its x-coordinate, or horizontal displacement from the origin, and its y-coordinate, or vertical displacement from the origin. Together, we write them as an ordered pair, indicating the combined distance from the origin in the form xy. An ordered pair is also known as a coordinate pair because it consists of x and y coordinates. For example, we can represent the point 3 and -1 in the plane by moving 3 units to the right of the origin in the horizontal direction and 1 unit down in the vertical direction. See Figure 4. When dividing the axes into equally spaced increments, note that the x-axis may be considered separately from the y-axis. In other words, while the x-axis may be divided and labeled according to consecutive integers, the y-axis may be divided and labeled by increments of 2 or 10 or 100. In fact, the axes may represent other units, such as years against the balance in a savings account, or quantity against cost, and so on. Consider the rectangular coordinate system primarily as a method for showing the relationship between two quantities. The Cartesian coordinate system. A two-dimensional plane where the x-axis is the horizontal axis, the y-axis is the vertical axis. A point in the plane is defined as an ordered pair, xy, such that x is determined by its horizontal distance from the origin and y is determined by its vertical distance from the origin. Example 1. Plotting points in a rectangular coordinate system. Plot the points -2, 4, 3, 3, and 0 and -3 in the plane. Solution. To plot the point, -2 and 4 begin at the origin. The x-coordinate is -2, so move two units to the left. The y-coordinate is 4, so then move 4 units up in the positive y direction. To plot the point 3, 3, begin again at the origin. The x-coordinate is 3, so move 3 units to the right. The y-coordinate is also 3, so move 3 units up in the positive y direction. To plot the point 0 and -3, begin at the origin. The x-coordinate is 0. This tells us not to move in either direction along the x-axis. The y-coordinate is -3, so move 3 units down in the negative y direction. See the graph in Figure 5. Analysis. Note that when either coordinate is 0, the point must be on an axis. If the x-coordinate is 0, the point is on the y-axis. If the y-coordinate is 0, the point is on the x-axis. Graphing equations by plotting points. We can plot a set of points to represent an equation. When such an equation contains both an x variable and a y variable, it is called an equation in two variables. Its graph is called a graph in two variables. Any graph on a two-dimensional plane is a graph in two variables. Suppose we want to graph the equation y equals 2x minus 1. We can begin by substituting a value for x into the equation and determining the resulting value of y. Each pair of x and y values is an ordered pair that can be plotted. Table 1 lists values of x from -3 to 3 and the resulting values for y. We can plot the points in the table. The points for this particular equation form a line, so we can connect them. See Figure 6. This is not true for all equations. Note that the x values chosen are arbitrary, regardless of the type of equation we are graphing. Of course, some situations may require particular values of x to be plotted in order to see a particular result. Otherwise, it is logical to choose values that can be calculated easily, and it is always a good idea to choose values that are both negative and positive. This is no rule dictating how many points to plot, although we need at least 2 to graph a line. Keep in mind, however, that the more points we plot, the more accurately we can sketch the graph. How to? Given an equation, graph by plotting points. 1. Make a table with one column labeled x, a second column labeled with the equation, and a third column listing the resulting ordered pairs. 2. Enter x values down the first column using positive and negative values. Selecting the x values in numerical order will make the graphing simpler. 3. Select x values that will yield y values with little effort, preferably ones that can be calculated mentally. 4. Plot the ordered pairs. 5. Connect the points if they form a line. Example 2. Graphing an equation in two variables by plotting points. Graph the equation y equals -x plus 2 by plotting points. Solution. First, we construct a table similar to Table 2. Choose x values and calculate y. Now, plot the points, connect them if they form a line. See Figure 7. Graphing equations with a graphing utility. Most graphing calculators require similar techniques to graph an equation. The equations sometimes have to be manipulated so they are written in the style y equals. The TI-84 Plus and many other calculator makes and models have a mode function which allows the window, the screen for viewing the graph, to be altered so the pertinent parts of the graph can be seen. For example, the equation y equals 2x minus 20 has been entered into the TI-84 Plus shown in Figure 8a. In Figure 8b, the resulting graph is shown. Notice that we cannot see on the screen where the graph crosses the axes. The standard window screen on the TI-84 Plus shows -10 is less than or equal to x, less than or equal to 10, and negative 10 is less than or equal to y, less than or equal to 10. See figure 8c. By changing the window to show more the positive x-axis and more the negative y-axis, we have a much better view of the graph and the x and y intercepts. See figure 9a and figure 9b. Example 3. Using a graphing utility to graph an equation. Use a graphing utility to graph the equation y equals negative 2/3 x minus 4/3. Solution. Enter the equation in the y equals function of the calculator. Set the window settings so that both the x and y intercepts are showing in the window. Finding x-intercepts and y-intercepts. The intercepts of a graph are points at which the graph crosses the axes. The x-intercept is the point at which the graph crosses the x-axis. At this point, the y-coordinate is 0. The y-intercept is the point at which the graph crosses the y-axis. At this point, the x-coordinate is 0. To determine the x-intercept, we set y equal to 0 and solve for x. Similarly, to determine the y-intercept, we set x equal to 0 and solve for y. For example, let's find the intercepts of the equation y equals 3x minus 1. To find the x-intercept, set y equals to 0. To find the y-intercept, set x equal to 0. We can confirm that our results make sense by observing a graph of the equation as in figure 11. Notice that the graph crosses the axes where we predicted it would. Given an equation, find the intercepts. Find the x-intercept by setting y equals 0 and solving for x. Find the y-intercept by setting x equals 0 and solving for y. Example 4. Finding the intercepts of the given equation. Find the intercepts of the equation y equals negative 3x minus 4, then sketch the graph using only the intercepts. Solution. Set y equal to 0 to find the x-intercept. Set x equal to 0 to find the y-intercept. Plot both points and draw a line passing through them as in figure 12. Using the distance formula derived from the Pythagorean theorem, the distance formula is used to find the distance between 2 points in the plane. The Pythagorean theorem, a squared plus b squared equals c squared, is based on a right triangle where a and b are the lengths of the legs adjacent to the right angle, and c is the length of the hypotenuse. See figure 13. The relationship of sides, x2 minus x1, the relationships of sides, the absolute value of the point x2 minus the point x1, and the absolute value of the point y2 minus the point y1 to side D is the same as that of sides A and B to side C. We use the absolute value symbol to indicate that the length is a positive number because the absolute value of any number is positive. For example, the absolute value of negative 3 equals 3. The symbols, absolute value of the point x2 minus the point x1 and the absolute value of the point y2 minus the point y1, indicate that the lengths of the sides of the triangle are positive. To find the length c, take the square root of both sides of the Pythagorean theorem. C squared equals a squared plus b squared, which gives us c equals the square root of a squared plus b squared. It follows that the distance formula is given as d squared equals the points x2 minus x1 squared plus the points y2 minus y1 squared, which gives us d equals the square root of the points x2 minus x1 squared plus the point y2 minus y1 squared. We do not have to use the absolute value symbols in this definition because any number squared is positive. The distance formula. Given endpoints, x1 and y1 and x2 and y2, the distance between the 2 points is given by d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Example 5. Finding the distance between 2 points. Find the distance between the points negative 3, negative 1, and 2, 3. Solution. Let us first look at the graph of the 2 points. Connect the points to form a right triangle as in figure 14. Then calculate the length of D using the distance formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. D equals the square root of 41. Example 6. Finding the distance between 2 locations. Let's return to the situation introduced at the beginning of this section. Tracy set out from Elmhurst, Illinois, to go to Franklin Park. On the way, she made a few stops to do errands. Each stop is indicated by a red dot in figure 1. Find the total distance that Tracy traveled. Compare this with the distance between her starting and final positions. Solution. The first thing we should do is identify ordered pairs to describe each position. If we set the starting position at the origin, we can identify each of the other points by counting units east, right, and north up on the grid. For example, the first stop is 1 block east and 1 block north, so it is at 1, 1. The next stop is 5 blocks to the east, so it is at 5, 1. After that, she traveled 3 blocks east and 2 blocks north to 8, 3. Lastly, she traveled 4 blocks north to 8, 7. And we can label these points on the grid as in figure 15. Next, we can calculate the distance. Note that each grid unit represents 1,000 feet. From her starting location to her first stop at 1, 1, Tracy might have driven north 1,000 feet and then east 1,000 feet or vice versa. Either way, she drove 2,000 feet from her first stop. Her second stop is at 5, 1, so from 1, 1 to 5, 1, Tracy drove east 4,000 feet. Her third stop is at 8, 3, and there are a number of routes from 5, 1 to 8, 3. Whatever route Tracy decided to use, the distance is the same, and as there are no angular streets between the 2 points, let's say she drove east 3,000 feet and then north 2,000 feet for a total of 5,000 feet. Tracy's final stop is at 8, 7. This is a straight drive north from 8, 3 for a total of 4,000 feet. Next, we will add the distances listed in Table 3. The total distance Tracy drove is 15,000 feet or 2.84 miles. This is not, however, the actual distance between her starting and ending positions. To find this distance, we can use the distance formula between the points 0, 0 and 8, 7. D equals the square root of 8 minus 0 squared plus 7 minus 0 squared, which is approximately 10.63 units. At 1,000 feet per grid unit, the distance between Elmhurst, Illinois to Franklin Park is 10,630.4 feet, or 2.01 miles. The distance formula results in a shorter calculation because it is based on the hypotenuse of a right triangle, a straight diagonal from the origin to the point 8, 7. Perhaps you have heard the saying, as the crow flies, which means the shortest distance between the 2 points, because a crow can fly in a straight line even though a person on the ground has to travel a longer distance on existing roadways. Using the midpoint formula. When the endpoints of a line segment are known, we can find the point midway between them. This point is known as the midpoint, and the formula is known as the midpoint formula. Given the endpoints of a line segment, x1, y1, and x2, y2, the midpoint formula states how to find the coordinates of the midpoint m. M equals x1 plus x2 divided by 2 and y1 plus y2 divided by 2. A graphical view of a midpoint is shown in figure 16. Notice that the line segments on either side of the midpoint are congruent. Example 7. Finding the midpoint of the line segment. Find the midpoint of the line segment with the endpoints 7, negative 2, and 9, 5. Use the formula to find the midpoint of the line segment. x1 plus x2 divided by 2, y1 plus y2 divided by 2 equals 7 plus 9 divided by 2, and negative 2 plus 5 divided by 2 equals 8 and 3 halves. Example 8, finding the center of a circle. The diameter of a circle has endpoints -1 and -4 and 5 and -4. Find the center of the circle. x1 plus x2 divided by 2, y1 plus y2 divided by 2 equals 2, -4. Access these online resources for additional instruction and practice with the Cartesian coordinate system. Plotting points on the coordinate plane, openstackscollege.org, find x and y intercepts based on the graph of a line, openstackscollege.org.